welcome to another lecture of ecology. This is a companion lecture to the one that you just watched or maybe watched a few days ago on aquatic environments. So I wore a companion dress. It's the same style by the same company, Tuesday Bassett, but this one has terrestrial animal on it. It's got a little moth and a little candle because it's like a moth to flame, and like the other dress, it also has moths on the back. Let's see if I can show you again. Some cute little moths. So, now let's head on to land and talk about animals on the land. And, well, we won't be talking about animals on the land yet, actually. We're just going to be talking about some of the physical and chemical properties that dictate the types of animals that will live in terrestrial environments. So let's get to it. Okay, terrestrial environments. This is a picture to introduce you to terrestrial environments. This is a picture I took in either 2016 or 2017 in Anza-Borrego Desert, which is when now I can't remember if it's 2016 or 2017, but there was a super bloom in the desert that year, and so I went out with the Woodard Lab, who I was working for at the time, to see the super bloom. So really unusual to see all of these flowers in bloom in the desert in Anza-Borrego. So in our lectures this week, in our in-person meetings out at Winnie Palmer, we're going to talk about the unique constraints that life on land imposes to organisms that live in it. But in this video lecture, first we're going to talk about how physical structures dictated by plants in an environment will affect the distribution of light vertically within an environment. So here we're going to compare and contrast a forest environment to a prairie environment, which we have small patches of both of these at Winnie Palmer. And you can we've experienced this firsthand during our first week back of classes, because I will only do stuff outdoors during a pandemic. In the trees, you probably felt cooler than you did when we were out walking around in the prairie, and that is because the canopy of the trees is going to absorb a lot of the light that's coming into the forest. And especially in a heavily forested area where the trees are pretty close together, and maybe there's lots of different species within an area. So maybe in this example here, there's several different species of trees here as compared to this one. You've got a lot of light absorption happening at the top of the canopy. So 79% of this light coming in is getting absorbed by the top of the canopy, and then only 2% is making it to the bottom. So really, all you have growing down here are shade-adapted plants. But in a prairie area, you're still getting a lot of light absorption by these taller prairie plants. So we can think about this when we're out at Winnie Palmer this week. You're still getting 36% of light absorption up here at the top, but a lot more light is coming through because it's not being blocked physically like it is in the forest. So you're also getting lowland clovers and other low-lying flowers in a prairie environment too. You also get seasonal changes in the amount of light availability at different heights, vertical distributions in an environment. This is kind of a lot of graph to look at in a short amount of time, so I will summarize it for you. So basically what you see here is that in August, September, June, July, and May, you've got really low proportion of light available at the bottom of the canopy. And then in November, December, January, February, April, and March, you've got higher light availability at the bottom of the canopy. Now, obviously, you get high enough, there's not really anything up there anymore. And so you've got almost full light availability at the top. But you see these seasonal differences because you might have noticed that at the high end of light availability, at the bottom, below the canopy, are in winter months. So maybe foliage looks like this, where it's starting to lose its color, and so the canopy is not absorbing as much light. Or into December and January, this is actually, I forgot to say, this is for a temperate forest in Indiana. So into January and February, some trees have no foliage, and so there is a lot higher light penetration into the ground floor. You have less light penetration in August, September, June, July, and May, because that's when trees have a lot of their foliage. And so that is going to increase the amount of light being absorbed at the top of the canopy and decrease the amount of light availability in the bottom. Now, all life on Earth depends on soil, and soil in environments is formed by weathering processes. So rocks and minerals erode to form soil. This is one of my favorite places that I haven't been to since I was a little girl when my family went out there for a family vacation, but it's still it's really, the images of it are still really sharp in my mind from when I visited. This is Bryce Canyon out west in the U.S. Beautiful place, and you can see prime examples of weathering here. So rocks and minerals will erode to form soil. You can have mechanical weathering, which is by physical breaking up, mostly by wind. So a lot of this is a mixture of mechanical plus chemical weathering, which is mostly facilitated by water. And water is the vehicle which aids in chemical reactions that happen within the rocks, and we'll talk about that in just a second. So soil formation involves 5 interrelated factors that we're going to talk about in depth here. Parent material, climate, biotic factors, topography, and time. And we're going to go into each of these. So parent material can be several different types of materials. It can be bedrock, like you see here. It can be glacial deposits. So the last glacial maximum, which I forgot to say in our second lecture when I was talking about ecological modeling, the last glacial maximum was about 25,000 years ago. And what that means is that that's the last period during which the glaciers in the world were at their largest peak. So the Earth was really cool and the glaciers were really large. During the recession of those glaciers, as the Earth warms, they leave behind deposits from their recession, and that's called till. You can also have sand and silt that can be carried by the wind. This happens more so in environments that are very dry because precipitation will wet the sand and silt down. But it can be really instrumental in soil formation. You can have gravity just moving stuff down a slope, which we'll see a prime example in one of my favorite places in just a second. This is obviously not happening a ton in Pennsylvania because we don't have a ton of elevational differences, but it can happen on small hills too. And then you can have sediments carried by flowing water. So when we talk about any minerals precipitating out of the ocean, especially if these are happening on coastlines, those can help in forming soil as well, especially if that ocean line is receding. So that was parent material. Let's talk about climate. The climate can have direct and indirect influences on forming soil. Direct climate effects would be things like temperature, precipitation, and wind, and then all those factors, that's a combination of chemical and mechanical weathering, break down the parent material to cause leaching. Like I said, water, you need water for chemical weathering because it's the vehicle which in chemical reactions are going to take place within the parent material. Temperature is going to control the speed at which those reactions occur. So if you have a warm temperature and more water, you're going to have more weathering, leaching, and plant growth. So something we'll talk about later on in the semester when we talk about nutrient cycling is that weathering and the soil formation processes happen really, really quickly in tropical areas because they have this combination of more water and higher constant temperature. And then indirectly, climate influences climate can influence it by influencing the plant and animals which live in the soil, and those, which we will also talk about in nutrient cycling, is that what plants and animals live in soils will also impact the nutrient cycling within soils. So if the climate is not hospitable to organisms which help degrade soil, then the nutrient cycling in soil will happen slower. So let's talk about biotic factors, since we started talking about that already. Like I said, plant roots help break up the parent material depending on how deep they can go. This tiny little guy is not doing that, but they help stabilize the soil surface too by providing these filamentous structures through them, and then they also bring up nutrients through the surface through the roots as well, which is really important for making those nutrients available to things that rely on the plants. Photosynthesis also is important in soil formation and nutrient cycling because it's going to turn any energy from the soil into organic carbon. And then a really important part of nutrient cycling that we'll talk about again later in the semester is decomposition. Microorganisms, bacteria, fungi, other microorganisms that live in the soils are going to be really important for decomposition and releasing nutrients into the soil. Topography can also affect soil formation. So this is one of my favorite places in the world. This is El Capitan at Yosemite. I didn't take this picture, but I lived there for 4 months in 2017, and I got to watch some guy climb this without ropes when I was there doing field work. It was terrifying, but this is a great example of how topography can affect weathering. So this is just an entire slope that's been affected by mechanical weathering, and probably also some sort of like large event that caused large pieces of this to fall off at some point. So this steep slope here is going to affect soil erosion and creeping down at the bottom, where you have a lot of pine, and also at the bottom in here where this picture was taken is in the Yosemite Valley. And so what happens up here comes down this steep slope and affects the soil composition in the Yosemite Valley. And then, of course, time is the fifth factor, because all of these factors assert themselves over time. Some of them take longer than others. So like the biotic factors are on a much shorter time scale. Things like weathering take millions and millions of years to form things like the Grand Canyon. So all of these things will affect soil formation more greatly over time. Soils are not all soils are created equally, and so soils are going to have some distinguishing physical characteristics. I really wanted to get one of these charts for us to use in lab, but these 2 pages alone cost $75, so we may not be using the Munsell color chart in lab, but we can, at least without it, look at broadly at color, texture, and depth. And in person this week, we're going to talk about how color, texture, and depth affect soil quality and the organisms that can grow in it. Let's talk a little bit about texture. So texture is going to dictate a lot of what amount of moisture can be held by the soil. So sandy soil doesn't have quite as high of a capacity for holding water, and is not nearly as stable for some plants, like we talked about with the mangroves that grow in the ocean. Sandy soil can only support certain types of life, mostly because it can't hold as much water. Now, loamy soil, on the other, is at the opposite end of the spectrum, and is very porous and can hold lots of water. And so you'll find this in high precipitation environments with a lot of nutrient cycling. We have a lot of this here, which isn't great for planting. I have tried to plant, it's not great for planting veggie gardens, but I've been trying in my own yard to make it mostly native, and so a lot of the species that I'm planting are adapted to clay soils because they're native to here. And clay doesn't hold nearly as much water because it's not nearly as porous. Now, during the process of decomposition and the breakdown of this bedrock, you get these distinct horizons that form in soil layers, and hopefully we'll be able to see some of these when we do soil core sampling in lab. And you can see most of these distinct layers, except for this one, in most soil around the world. So we'll start with the O layer, which stands for organic layer. So this is mostly organic material. This is the stuff that's got the nutrients that have been released and are mostly available to plants and microorganisms in the environment. So it's mostly undecomposed or partially decomposed plant materials. So this is like dead stuff that's happening up here. Then you've got topsoil, the A or horizon. So this is mostly mineral soil. Derived from the parent material. Organic matters leached from above give it like this distinct dark color. Now we may not be able to see all of these layers depending on the types of soils that we sample in lab. And then you have the subsoil. This is where you're going to have accumulation of mineral particles like clay and salts that are leached from the topsoil. And this is going to be, again, different in color and structure. And then you have the bedrock material, which usually our soil cores that we have for lab are not going to be long enough to sample bedrock. And our bedrock here is mostly limestone, I think. I'm not sure about specifically at Winnie Palmer, but yeah, we wouldn't be able to sample it anyway. And so as this bedrock decays or weathers, you can see different levels in breakdown as you go up in the horizon layers of the soil. Ion exchange capacity is also really important for how fertile a soil is going to be and what kind of plant growth it can support. So the mineral composition of the bedrock is going to really affect the cations that are present in the soil. So like I said in the previous lecture, we have a lot of limestone in Pennsylvania. And when that limestone leaches naturally into waterways and then into soils, it should make the balance out the pH of the soils around here. But we also have mining, and through mining you get a lot of leaching of acids out of different types of bed material and other things that would not naturally be exposed, and that can make the soil more acidic. And like I said before, at high acidities, aluminum becomes soluble in water, and that makes it really, really toxic to plants. And so just the last thing on soil before this short little mini lecture is over is I want to talk about 5 main processes for forming soil. So you've got laterization. This is when you have hot, rainy conditions that cause really rapid weathering of rocks and heavy leaching. So this makes the soil more acidic. This can be a natural process, but this is also a little bit of what we have going on with acid mine drainage. You can have calcification. This is when evaporation and water uptake by plants exceeds the amount of precipitation that you're getting in the environment. And so because of that, salts start to precipitate out of the soil, mostly calcium carbonate, and that makes the soil more alkaline. So I have a picture here of one of these alkaline soil environments. This is these are alkali bees that live in Oregon in this alkaline soil, and this is a huge aggregation of them. Like they're just massive amounts of bees living in the soil here, and they're called alkali bees because this is alkaline soil. There's also salinization, which is similar to calcification. It occurs in drier climates and at the top of the soil, so very similar. And then you have podzolization, which is this is a very specific kind where if you have coniferous vegetation, so pine trees and things like that, those leaves are very acidic. That helps them a little bit. Their evergreen trees have very acidic leaves because it helps a little bit protect them from cold temperatures in the winter. But when they lose those pine needles and those pine needles decay, they release a lot of acids into the soil, and that creates this sand layer in the A horizon. And then you have glaciation, which when you get high rainfall or low drainage, it makes the decomposition slower, which makes the soil a bluish gray color. So when we sample, we might see this bluish gray kind of clay layer when we sample in the wetlands on campus. We definitely see it if we were going out to Spruce Flats Bog, but we can't do that this year. So and we'll see that in the wetlands and in bog areas and stuff like that because there's really low drainage, and because the area is so waterlogged, it is slowing down the cycling of nutrients because it's not getting oxygen, which we'll talk about later. So that's it. A little short mini lecture on soil. Tune in for week 3. Bye-bye.